Hello, hi. Okay, so last time we saw that you can best describe vector spaces, subspaces, or spaces in general, best describe vector spaces as a span of a collection of members. So all linear combinations of a collection of members, which is called a span. So the check-in here today is trying to illustrate that important idea, is that you can express any member of that space, the collection of a plus bx plus cx squared, where b plus 2c is equal to 0. You can express any member of that space as a combination of members of the set S there, where it says 1 comma minus 2x plus x squared comma and 3 minus 4x plus 2x squared. So I'm going to write down three members of the space, and you might remember them, they're the members from last time. I'm going to write down three members of the space, and I'm going to express them as linear combinations of members of S. That is to say, S is a spanning set for the space. Okay, let's give it a try. So let's see here. The first one from last time, I'd better write down S because I'll forget. So the space is A plus bx plus cx squared, where b plus 2c equals 0. And S was, what the heck was it? It was 1. That's 1 plus 0x plus 0x squared. So it's a perfectly good member of the space. Minus 2 plus x squared, minus 2x plus x squared. And then 3 minus 4x plus 2x squared. If I remembered it right, if I wrote it down right. And the very first one was, it was 5 minus 8x plus 4x squared. And the basic idea here simply is I'm going to write that as something times the first member plus something times the second member plus something times the third member. And it's just a question of coming up with somehow what it is that you want to do and just doing it. So I'm going to fill these parts in one, and I use a pencil to dramatize that. I'm filling these parts in. So for example, I see the 2x squared and I see the 4x squared, so I'm thinking to write a 2 there. Not the only thing a person could think to do, but that's what I thought to do. And if I put a 2 there, the 2 times 2 becomes a 4. That's what I'm looking for. The 2 times minus 4 becomes a minus 8. So good, got lucky there. 2 times 3 becomes 6. I don't want a 6, I want a 5. So how about if I put a minus 1 here? And then I guess a 0 there. So I express this member of the subspace. Perfectly good member of the subspace. It satisfies the condition. I express this member of the subspace as a combination of 3 of these. Happens not to need any of these, but it's a perfectly good combination. Minus 1 of the first, 0 of the second, 2 of the third. Okay. Next one, I'm trying to remember what I had last time. Next one was minus 2, minus 6x, and then plus 3x squared. And again, with the fill in the blanks. Okay, I didn't quite make it on the sheet. So I don't know what to do here, but I guess I'll come up with some numbers and see how it goes. I think I tried when I wrote this down while I was thinking about what I wanted to say here. I wrote down a 1 and a 1 because I'm trying to illustrate that I can sneak this second guy in there if I want to. So if you put a 1 there and a 1 there, then you get 1 times 2x squared, and 1 times x squared makes a total of 3x squared. That's what I wanted. Now when I put the 1 there and the 1 there, I also get a minus 4x and a minus 2x, so that's a total of minus 6x. Good. And I get a 3 and a 3 and a 0. 3 and a 0, so that's 3 so far. And how many of these do I need? I guess I need minus 5 of these. Okay, did I do that right? So 3 and 0 minus 5 makes a total of minus 2. I think I did that right. And then the last one, just again to illustrate here, I'm looking for, what the heck was it? It was 4 plus 10x minus 5x squared. And again with the blanks, I know it's annoying if you do too much of it, but I'm trying to leave, of course, a visual impression, and so I'm putting visual symbols down. Okay, and I guess here, what the heck do, so, I guess, what to do, I'm gonna put a minus 5 there to pick up the minus 5x squared. Okay, if I put a minus 5 there times the minus 2 makes a positive 10, so I get the 10 automatically, so I don't need this x squared and that x. I don't need it. So minus 5 there and a 0 there. And what am I going to do for the constant term? Why, this doesn't have a constant term. This has a constant term, but it's multiplied by 0. So this doesn't have a constant term, so I don't need to worry about it. So I think if I put a 4 there, I think I'm in business. So I think I'm in business. Okay, so what I found is that I can, by just thinking about the numbers, not the letters yet, but I can write any member of the space. This is the 3 I tried, but I can write any member of the space as a combination of those things. So that was the first question. Then the second question, I forgot the second question already, is, observe that the third member of S is a combination of the other two. 3 minus 4x plus 2x squared is a combination of the first two. Yeah, it is. Yeah. And then it says use that to express V1, V2, and V3 as combinations of just the first two members of S. So it turns out I didn't need this third member. I could have got away without it. I could have made the spanning set even smaller, and I still would have been good. Okay, so what 3 times 1 minus 2 times, okay, so I better write that down because I'll forget. So I have 3 times, 3 times 1 minus 2 times, no, plus 2 times minus 2x plus x squared makes the third one. 3 minus 4x plus 2x squared. Yes, that's right. Okay, and this is just a question of noticing that I can go up and take, I'll just take the second one, just to illustrate something. I'll take the second one. I can take minus 2 minus 6x plus 3x squared, take the expression that's written there, minus 5 times 1, plus 1 times minus 2x plus x squared, plus 1 times 3 minus 4x plus 2x squared. Rewrite that as minus 5 times 1 plus 1 times minus 2x plus x squared plus 1 times, I'm going to copy, of course, this right into this blank space here, 3 times 1 plus 2 times minus 2x plus x squared. And now I'll combine the ones and combine the minus 2x plus x squareds, and what do I get when all the smoke clears? There's 5 and there's minus 5 and there's 3, so I'm ending up with a minus 2 times 1. And how many minus 2x plus x squareds are there? 1 and 2 more makes a total of 3. And I better check. So minus 2, yes, that's right. What about coefficients of x? Minus 6, that's good. What about coefficients of x squared? 3 and 3, so that's right. Now obviously the same trick would work, the same technique would work for the other two. That is to say, you can expand the third term and get rid of the third term in some sense, get instead a combination of the first two, and you don't need the third term. You can boil it down to the first two, so you can get by with a smaller spanning set. If some member of the spanning set is a combination of the others, why, you can get rid of it. Okay, so the check-in is some practice The check-in is some practice with spanning sets and is making a point about parameterization here and making a point about how you can express a vector space, subspace, or any vector space at all using somehow these members of the spanning set. Members of the spanning set. Okay. Whoops, what happened here? Oh, I'm in the wrong place. Sorry. There we go. Linear independence. So I want to introduce an idea here based on what we talked about in the check-in. I want to introduce an idea here, and I know the last video was pretty long. Fortunately, this one's relatively short. I want to introduce an idea here that talks about having somehow a minimum number of members of those spanning sets. So I have to define the term, and then we're going to see that it relates to a minimum number. So in any vector space, set of vectors is linearly independent if none of its elements is a linear combination of the others. Linearly independent. So in the check-in, we saw that the third member of the spanning set was in fact dependent on the other two. You could express the third member as a linear combination of the other two. So we would have said, now with the vocabulary that we have now, we would say that the set I started with, the three-member set, was linearly dependent. When you cross that third member out, then the remaining two are independent. You can't express the one as somehow a multiple of the other. I want to make a point here about linear independence and linear dependence to start out. It's very often the case in mathematics that you see a definition that tries to capture somehow the concept of what independence and dependence is. Linear independence is when none of its elements is a linear combination of the others. But then a lot of times you'll follow up a definition like that with a lemma or a small result that says to compute whether something is, in this case, whether something is linearly independent. Here's the most convenient way, and that's exactly what's happening. If I write a vector as a linear combination of the others, if I write S0 as a linear combination of the S1 through Sn, visually I've set S0 off, but in fact algebraically I've got a kind of an unbalanced situation there because I have one vector being treated differently than the others. It's algebraically convenient here to move it over to the other side of the equation and get 0 on the left and then just some combination of S0 through Sn on the right. And basically here, if you have a combination on the other side, if you have a combination on the right-hand side of all these vectors, these SIs, you can, in fact, if you want to, move it over to the left and get isolated, or you can think of it as all being on the same side and 0 on the other side. When we don't want to single out one vector as sort of different than the others, and we often won't, when we don't want to single out one vector as sort of different than the others, what we'll say instead is that they're in a linear relationship, and we'll write them all on the same side. And that proves to be convenient here. If you write all your vectors on the same side and then equals 0, that will prove to be the most convenient way to check whether a subset is linearly independent or not. Okay, so I'll read it. A subset of a vector space is linearly independent if and only if, among its elements, the only linear relationship, I have the s's on one side of the equation and 0 on the other, is the trivial one, namely all the ci's are 0. Okay, and I'm assuming that si is unequal to sj. So the point here is that I defined a concept that no one is a combination of the other folks. And then I immediately followed it with a lemma that says, here's how to compute. If you're given a set on the homework, and your question 1 says, here's a set, decide whether it's linearly independent. You write it in this form here. You write it as all the vectors on one side, a linear combination of all the vectors on one side, and 0 on the other side. And then you see whether that implies that the only vectors, the only combination that works is to have all the coefficients, the scalars, the ci's, equal to 0. Okay, now I gave a proof, but do we really need a proof? Is that if S is linearly independent, then there's no linear relationship where some of the S's have non-zero coefficients, because otherwise you could move everything to one side of the equation and get that SI all by itself and you'd have a combination. And vice versa here. If S is not independent, then you have Si is some combination of the others. And when you move it over to the other side of the equation so that you get 0 on the left and the Si is in there on the right side with the others, why you have some collection where there's a linear relationship and not all of the CIs are 0. It's okay if some of them are 0, but not all of them are 0. Not all of them are 0, it says up here, would tell you not independent. Okay, so to decide whether a list of vectors is linearly independent, what happens is you set up the equation, you put 0 on one side, and you write a linear combination of the SIs on the other, and you do what it takes to figure out whether any solution exists other than all of the CIs are 0, other than the trivial solution. High time for a numerical example. So here's two vectors in the plane, and they're linearly independent. You can tell at a glance that neither of them is a combination of the other one. What do you do here to follow the lemma? And the answer is to follow the lemma, you set up a linear combination of those vectors equals to 0. And you ask yourself, can I find a C1 and a C2 that are not both 0? And of course, at a glance, you see, no, you cannot find such a C1 and C2. No. And you also get a hint that what's going to happen here is we're going to get linear systems, and we'll solve the linear systems. Another example, we'll try and have a sort of the first one was very easy, the second one is a little less easy, but not all that hard. I have a set 1 minus x and 1 plus x that is a subset of the collection of cubic polynomials. Well, this is a cubic polynomial, this is a cubic polynomial, fair enough. And I'm asking, is it linearly independent? And of course, the question says it is linearly independent. So to prove that, I set up a combination of the two members of the set. They're vectors because they're members of a vector space. I set up a combination of the two vectors, set it equal to, that's the 0 polynomial. 0 plus 0x plus 0x squared plus 0x cubed. So don't get confused. That's the 0 member of the space. So there I go. I have a linear combination of the two on the left, and I have the 0 polynomial on the right, and that leads me to what's the constant term on the left, what's the constant term on the right? That gives me an equation. What's the coefficient of x on the left, what's the coefficient of x on the right? That gives me an equation. There's also an equation for x squared and x cubed, but it just says 0 equals 0, so I left it out. When you look at this system, C0 plus C1 equals 0, minus C0 plus C1 equals 0. We've done a lot of these. A person can tell, this is not one that you need to go through Gauss's method, a person can tell at a glance that the only solution is C0 equals 0 and C1 equals 0. So the lemma says if the only solution is the trivial one, then you write down the word independent. If there's any other solution, you write down the word dependent. All right, another example, trying to have a wide variety of examples. Important idea, but we want to focus just on the one idea today. So wide variety of examples. The rows of this matrix. The rows of this matrix form a linearly independent set. Can you write down C1 times the first row plus C2 times the second row plus C3 times the third row? We won't worry about the zeros there. Can you write down C1 times the first row plus C2 times the second row plus C3 times the third row and get the zero row vector 0, 0, 0, 0, 0? Can you write down, is there a non-trivial collection of C's that gives you that? And of course no. If I were to write down here, if I were to write down, if I can hit my buttons there, if I were to write down C1 times the first row plus C2 times the second row plus C3 times the third row, and I ran out of space, equals the 0 row. Let me remind myself what the parts are. It is 2, 0, 1, minus 1, 2, 0, 1, minus 1, 0, 1, minus 3, 1/2, and 0, 0, 0, 5. If I write down that equation, then I think, of course, I can do Gauss's method. I can set up the system of first components, the system of second components, the system of the equation, excuse me, of second components, the equation of third components, and the equation of fourth components, and I get a homogeneous system. Or you can just apply your noggin, just apply your noggin. Look at the equation of first components. C1 times 2 plus 0 equals 0. You conclude C1 equals 0. I mean, nobody. I'm not providing any penalties for being smart enough to see the answer, and a person could just see the answer. Sometimes with these linear systems, you have to apply Gauss's method. It's just too hard, but this is not in that category. Knowing that C1 equals 0, look at the equation. Look at the combinations of second components. Because C1 is 0, I can cross that off and no longer have to think about it. I'm looking at C2 times 1 plus 0 equals 0. Okay, so C2 equals 0. Sort of stuff. We get that C0, C1, C2, and C3 are all 0, and so I get that the only solution is the trivial one, and so I'm looking at linear independence. This subset of R3 is linearly dependent because when you take C1 times the first plus C2 times the second plus C3 times the third, you get a linear system, and it has more than just the trivial solution. Whoops, excuse me, more than just a trivial solution. So that's the only case. Okay, so that ends the day. We're interested here in figuring out when these systems have more than just a trivial solution, that's linear dependence. When they have only the trivial solution, that's linear independence. And we'll talk more about it next time. Okay, very good. Bye-bye.